Hi, thanks for attending. This is my third talk, so I'm sure you're very tired of hearing my voice by this point. If you've stuck around for all three talks, well, thank you very much. You are now qualified to be my new PhD student, and we'll proceed next to interviews. Sorry. This is our entry for the challenge track, or the challenge case track, where we present a case example to the SBSE community and make a case for how it can lead to innovation in this community. Largely, this is admittedly an advertisement for our new release, Defects4J 2.0. I know many of you have used Defects4J before. For those who are new, this talk should serve as a quick introduction and hopefully entice you to use the dataset in your own research. For those familiar, this is our announcement to check it out again as we've introduced some major changes. Each year, the Symposium on Search-Based Software Engineering hosts a challenge track. This track presents a series of cases often centered around particular software systems or research domains, and tasks researchers with applying their research to those challenge cases. This track has attracted great attention and great competition, and has been a powerful mechanism for highlighting the applicability of state-of-the-art research to complex real-world problems. We propose that Defects4J can serve as a compelling challenge case for future editions of this conference. Defects4J is a collection of reproducible bugs extracted from real-world Java software systems together with a supporting infrastructure for using those bugs. It's available at defects4j.org. And the current release 2.0, which just came out recently, targets Java 8 and contains 835 bugs from 17 Java software systems, as well as supporting infrastructure for conducting experiments in software testing and debugging research. These 835 bugs span more than a decade of development history, and the 17 projects span a wide range of domains, including compilers, parsers, testing infrastructure, and a variety of libraries. Defects4J has been used to evaluate automated test generation, automated program repair, and fault localization research. And past contributions to the challenge track at this conference have expanded the dataset, adding Mockito and JSON. The inclusion of Defects4J in the challenge track can serve as a benchmark for software engineering research, as well as a catalyst for new innovations. What do we require from these bugs? Well, each bug in Defects4J has the following three properties. First, each bug consists of a buggy and fixed source code version. The fixed version is explicitly labeled as a fix to an issue reported in the project's issue tracker, and the changes imposed by the fix must be to the source code and not to other project artifacts like configuration or build files. Second, every bug is reproducible. All tests pass on the fixed version, and at least one of those tests fails on the buggy version, exposing the bug. And third, each bug is isolated. The buggy and fixed versions differ only by a minimal subset of changes, all of which are related to that bug. That is, the difference is free of unrelated code changes like refactoring or feature additions. When we add bugs to Defects4J, we perform a manual cleaning process to ensure that the unrelated code changes are removed. And for each bug, Defects4J provides a few pieces of information, some metadata and the following artifacts: a pair of source code versions, the buggy and fixed versions, a set of classes and source code lines modified by the patch that fixes the bug, a set of developer-written test cases that expose the bug, we call these the trigger tests, a stack trace for each trigger test when executed on the buggy version, a set of classes loaded by the class loader during execution of the trigger tests, a set of tests that are relevant to the bug, tests that load at least one class, modified by the patch that fixes the bug. And to support use in research experiments, Defects4J offers a command line utility to execute a set of common tasks for each bug, including the following. You can print information about a bug, you can check out the bug or the fixed source code version, you can compile a source code version, you can execute test cases and optionally monitor the class loader, you can evaluate bug detection, perform coverage or mutation analysis, export metadata like class paths, directories, and sets of tests. And by default, Defects4J commands use the developer-written tests that come with each project. However, each command can be executed for an arbitrary JUnit test suite, including those you might create with an automated generation tool. Now, on that note, Defects4J offers a uniform interface for automated test generation with concrete instantiations provided for EvoSuite, a search-based test generator that I'm sure most of you are aware of, and Randoob, a feedback-directed random test generator. Defects4J also provides a template to ease incorporation of additional test generators into that infrastructure. Now, Defects4J can be expanded along different dimensions. First, testing and debugging tools can be integrated into the supporting infrastructure through well-defined interfaces. Second, a semi-automated process supports mining candidate bugs from an existing project's version control system and issue tracker. This process requires the creation of a meta build file that can compile any source code version of the project, generally by calling an existing build script. An automated step mines candidate bugs by cross-referencing the project's version control history with its issue tracker, identifying commits that fix a reported and closed issue. This step also compares each fix commit with its predecessor commit to determine whether at least one trigger test exists that reliably passes on the fixed version and fails on the buggy version. Each reproducible bug is then subject to a manual minimization process that eliminates irrelevant code changes like refactoring or feature additions. Finally, an automated step adds all reproducible, minimized bugs to the dataset and computes the metadata. Now, Defects4J can serve as a challenging and diverse benchmark for search-based software engineering research, as well as a catalyst for new innovations. Past research has successfully used Defects4J to evaluate software testing and debugging approaches, effectiveness of automated test generation and its corresponding fitness functions, automated program repair, and fault localization. I'm going to highlight quickly 3 concrete areas in which Defects4J can serve as a challenge case, as a benchmark for empirical evaluation as part of novel search-based software engineering techniques, and where search-based software engineering researchers could expand the scope and utility of the dataset. Right? So first, we can look at how Defects4J can be used to validate and extend work that was presented in prior editions of the Symposium on Search-Based Software Engineering, and how it can be used to explore new search-based software engineering approaches. This is not an exhaustive set of areas by any means, but it's intended to provide some level of inspiration. So first, genetic improvement. Search-based approaches have been used to improve system performance, and these performance improvements should be semantics preserving, so they should not alter the functional behavior of the system. Defects4J can support the empirical validation of performance improvement research by providing a supporting infrastructure for integrating tools and a thorough set of tests for assessing the generated patches, just like we do in automated program repair already. Second, hyperparameter tuning. Search-based approaches often have many parameters that can and need to be tuned to increase effectiveness on particular problem instances, like the crossover and mutation rates of a genetic algorithm. A fair and comprehensive assessment of automated tuning processes requires a well-defined dataset. We provide such a dataset, foster replicability of experiments, and support validation of in-project and cross-project generalization of hyperparameter settings. Third, longitudinal studies and software evolution. So software evolves over time, and Defects4J's artifacts capture this evolution. With a diverse set of projects and multiple artifacts per project, spanning multiple years of development history, we support longitudinal studies that investigate the effectiveness and generalizability of search-based approaches over time. And fourth, test suite diversity. Prior work hypothesized that diverse test suites are more effective than those that contain similar tests. Well, we support controlled experiments that can assess the impact of increased or decreased diversity on fault detection. The use of a common dataset also offers common grounds for researchers to compare different diversification techniques. Defects4J can also form an integral part of new search-based software engineering research. For example, predictive modeling. Search-based approaches can be used to tackle prediction problems, like defect prediction. The 835 bugs in Defects4J correspond to over 1,000 buggy Java classes. Features of those classes and the isolated bugs themselves can be used to develop or train predictive models. Second, state space exploration and program repair. Search-based approaches for automated program repair often have difficulty traversing the search space due to a costly fitness evaluation. So recent work addressed that challenge by capturing dependencies between source code statements and high-level differences between patch variants. Defects4J is a natural benchmark for novel program repair research, as this dataset includes both buggy and fixed versions of a variety of complex bugs. Third, topic modeling. Recent work has examined the extraction of information from textual artifacts like bug reports, and Defects4J provides many examples for topic modeling and can serve as a basis for linking code and textual artifacts. Since each bug in Defects4J is linked to a bug report, and the project and classes themselves often include detailed documentation, right? So these topics that I've mentioned capture only a portion of the research presented last year, the 2019 Symposium on Search-Based Software Engineering. Defects4J can also support other research areas such as crash reproduction by providing trigger tests, detailed stack traces, and isolated bugs, all of which can be used to assess crash reproduction approaches, or mutation testing. The Defects4J's real bugs can serve as templates for evolving new mutation operators and new mutant generation techniques. Finally, extending Defects4J also poses interesting challenges that may inspire new approaches. In particular, automated build script creation and repair. Adding bugs to Defects4J currently requires the manual creation of a meta build file. Genetic programming could be used to automate this step. Some of the associated challenges include gathering dependencies and inferring the necessary properties to build each source code version. Second, new projects and bugs. The set of systems in Defects4J is fairly diverse, but many domains are not accounted for, and new projects and new bugs for existing projects would increase the range of research that could be supported. Of particular interest are AI-based systems, concurrent systems, and systems in other difficult-to-test domains. We are also interested in new test generation approaches. We include a standardized interface for automated test generation. This interface allows researchers to quickly integrate and evaluate new approaches. An interface would also be interesting to add for automated patch generation. Just like the standardized interface for test generation, we would benefit from a well-defined interface for tools that generate patches, including tools for automated program repair and genetic improvement. A standardized interface for executing these kind of tools would help us facilitate reproducibility and comparability of techniques. In addition, automated support for newer versions of Java would be ideal, as new versions of Java may result in unexpected compilation errors, test failures, or metadata inconsistencies. So novel approaches for automatically migrating source code and tests to newer Java versions would be a welcome contribution. In addition to these examples, there may be other needs and challenges that require attention to support different research areas or experimental protocols that we do not already cover. So we propose that Defects4J can serve as a challenge case for search-based software engineering research, as well as a catalyst for new innovations. So what can you do with this benchmark? We look forward to seeing the results at the next edition of the Symposium on Search-Based Software Engineering. At the same time, we are interested in knowing how the benchmark can better evolve to support your research, so feel free to reach out to the email addresses below or file an issue on our GitHub with your suggestions. I would welcome any questions.